Okay, so now in order to justify the remark that I just made, I owe you an example of a function and a point in the domain of that function where that function is continuous but not differentiable. And that's exactly what this example is going to give you. Okay, so our function is the absolute value function, and the point in its domain is x equals 0. And this example says that we are expected to show that that function is not differentiable at the point 0. So, by the way, if you're ever asked to do this and you're asked to show that a function is not differentiable at a certain point, you would start by just trying to calculate its derivative at that point. And really, in the end, you're going to get a limit when you write out the formula for a derivative at a point. You're going to get a limit, and really you're just expecting that limit not to exist, and it's up to you to show that that's the case. So let's start that way. We're going to start by calculating f prime of 0, and we're expecting to get a limit that doesn't exist. Okay, so start by using the formula, limit as h goes to 0 of f of 0 plus h minus f of 0 all over h, right? We're just using this formula here in the case where a is equal to 0. So we're just using this formula, but plug a equals 0 in, and then this is the limit we just wrote down. Okay, well, what's f of 0 plus h? Well, f is this function up here. So if you plug 0 plus h in here, you're going to get the absolute value of 0 plus h. And then if you plug in 0, f of 0 is going to be the absolute value of 0. And all of this is going to be divided by h. Okay, well, what do we have here? Absolute value of 0 plus h, that's just the absolute value of h. And then, of course, minus the absolute value of 0. Absolute value of 0 is just 0, so you can just forget about this whole term. So really, we just have the absolute value of h over h. And now this is something we've seen before, but just with a different variable. I'm going to pull up a page from the section 2.3 notes where we calculated the following limit. We calculated the limit as x approaches 0 of the absolute value of x over x. And, well, you might say that's a weird way to word it. We didn't calculate it. We showed that it didn't exist in this case. And how did we do that? Well, we took the limit as x approaches 0 from the left, and we worked it out carefully, and we got -1. We took the limit as x approaches 0 from the right, and we worked it out carefully, and we got +1. So the two one-sided limits in this case don't agree. One gave us -1, the other one gave us +1. So whenever that happens, you can conclude that the two-sided limit does not exist. And that's exactly what we did back here. And remember, that's the limit as x goes to 0 of the absolute value of x over x. What do we have here? The limit as h goes to 0 of the absolute value of h over h. It's the same limit with just a different variable. So whatever this limit resulted in is exactly what this limit is going to result in, right? Which is that the limit doesn't exist. So this limit doesn't exist either. Okay, so that means, therefore, f is not differentiable at x equals 0. That's our conclusion, right? And if you want, we can put a box around it. That's what we're asked to show, and that's our conclusion, so we can identify that we're done the problem. And by the way, let's just draw, we can sneak a picture in here. Don't need to make it too huge. This is a fairly straightforward graph to draw. If you graph a sketch, or sketch a graph of f of x equals the absolute value of x, you get this picture. Right, you get that. Right, it's like a V. It goes up this way at a 45-degree angle, and it comes down here at a 45-degree angle. That's just a sketch of the graph of y equals the absolute value of x. So what did we really identify here? Well, right at this point, the function is not differentiable. Right? That's what our conclusion was over here. At this point, the function doesn't have a derivative. So what does that mean geometrically? Well, if this existed, f prime of 0, if we actually got a limit that existed and gave us a number, what would this give us? It would give us the slope of the tangent line to the graph of f at the point 0. In other words, it would give us the slope of the tangent line at this point. Well, it doesn't even make sense to draw a tangent line at this point. Right? Let me use my ruler to highlight that fact. If you have a nice curve, a nice smooth curve and a point on that curve, you can say there's a unique tangent line, a unique line that touches that curve at exactly one point. But look at if I angle my ruler like this, you could say that that's a line, and maybe I'll just draw it in red. That's a line that hits that point, or hits that curve, quote unquote curve. Really, it's not really a curve, but it's a graph of a function, right? This red line hits the graph at exactly one point. Does that mean it's a tangent line? Not really. Not when it looks like that. Not when it's got a sharp corner, right? Because then if it was a tangent line, so would that be. That would be a tangent line too. And I could keep going. I could draw lots, right? I could draw lots of lines that touch the graph at exactly that one point. So the problem is the tangent lines have to be unique for that limit to exist, right? And in this case, the tangent line is not unique. There are countless different lines I could draw that touch the graph of this absolute value function at a single point. So that's the reason. And so the problem is the graph is not smooth here. At x equals 0. Okay, that's going to be a really important word, the word smooth. Really, that's your descriptive word to describe differentiable. To say a function is smooth at a point is exactly the same as saying it's differentiable at a point. Okay, it's just another way to phrase it. But being smooth at a point means you don't have sharp kinks or corners or bends like this, or cusps. You have a nice smooth arc, like a parabola, like our parabola did in the previous example. Okay, so this is geometrically what it means when that limit doesn't exist. When this limit f prime at a certain point doesn't exist, but the function is continuous, it usually means there's a sharp bend or a kink at that point. Okay, next we're going to talk about the derivative as a function. Remember back to in section 2.1, we first introduced the idea of instantaneous velocity at a point, which really that's what this is the abstraction of, the derivative of a function at a point. Right? This is kind of like in the case where your function f happens to be a position function, well then this is going to give you the instantaneous velocity at the point A. Then after that, we introduce the idea of the velocity function. So a function that gives you the instantaneous velocity of an object moving in one dimension at every single point in time t. The derivative as a function is going to be an abstraction of that idea. Okay, so that's what we're going to define next. So the derivative of a function f is defined by, and just before you object and say, didn't we already define the derivative? We kind of did at the beginning of this section, right? We defined the derivative of a function f, but this was at a particular point, right? We defined the derivative of a function f at a point x equals a. So this is a derivative at a point. But now we're talking about the derivative as a function. So it's just the derivative of f. And you don't need to add any more to that phrase to say what you mean. So we're talking about the derivative as a function. And here's how you define it. Okay, so we take the limit as h goes to 0. It's going to look an awful lot like this definition, except the only difference is instead of talking about a particular point a, a particular point x equals a, we're just going to say at x. It's just going to be a function of x. So the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So you see that looks a lot like the limit in this definition, except instead of an a, we have x everywhere, right? So guess what we're going to write for the notation for it? We're going to write f prime of x instead of f prime of a. And it's really nothing new. It's just not looking at a particular point at a time. You're just talking about the derivative as a function. So this is our new function f prime. And note, you can add in the following. I'm going to say the domain of f prime is just going to be the set of all numbers x, which happen to be in the domain of f, such that f is differentiable at x. Okay, so in other words, is differentiable at the point x. Okay, so it's the set of all points at which you can take its pointwise derivative. Okay, so I just snuck that in there. I want to put a box around it just so it gets clearly separated from the other writing nearby. Okay, so that's because every function has a domain, right? And the derivative of a function is again a function. So f prime is the function. So I can write domain of f prime to actually state what the domain of that function is. So if you want to determine if a point is in the domain of f prime, just calculate the function's derivative at that point. And if you get a limit that exists, then you know you have a point that is in the domain of f prime. But otherwise, like for example here, if you wanted to talk about the derivative of this function as a function, this work justifies the fact that 0 is not in the domain of the derivative of this function if we were to consider it. Okay, let's do another example where it gets a little trickier to actually compute. Not much trickier, but it is a little bit more work. But here we're talking about this is also going to serve as an example where we can find the derivative of a function. Here's the function f of x is equal to x cubed now, but notice no point is specified. We're asked to just find its derivative. We were asked to find the derivative at a particular point, like we did in other examples. We're just finding its derivative as a function. So we're going to use this definition, right? And this is, this is so important. I want to put a red box around this too, because this formula is really one of the key formulas in this entire course. So this is really important. So put a box around that too, put a star by it. You're going to want to have that handy for the next little while because you'll need to look it up quite often maybe to use it, because you will use it often. Okay, so let's use that here. So we're gonna start by just computing f prime of x, because that's what it means to find the derivative of this function. Okay, so we'll use the definition in this formula. This is what we're going to use. So we're going to have the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so that's our first step. And our second step is going to now be to actually unwind what the function does. So f of x plus h, plug x plus h into this function. So you're going to get the limit as h goes to 0 of x plus h all cubed minus x cubed. So that'll be your numerator, right? Because this is f of x is x cubed. That's here, and then we'll have h on the denominator. Okay, so what's going to happen? Well, if you plug in h equals 0, you're going to get x plus 0 here. So you'll have x cubed minus x cubed, which is just 0. And of course, h on the denominator, you'd have 0 downstairs as well. So it would be a 0 over 0 type. That's no good. We're going to have to do something else. But this is actually very similar to the case where when we dealt with x squared. It's just that we have a higher exponent to deal with, right? This is a factored cubic, but then we've also subtracted an x cubed afterwards. So it makes sense to maybe we should expand everything out, combine like terms, and then try to refactor it after, and maybe something nice will happen, right? And in fact, that's exactly what's going to happen. But it's something, as far as why you should try it, you should notice that you've got a polynomial on the top. Like, you know it's going to be a polynomial. If you treat h as a constant, it's going to be a polynomial in the variable x. But it's not completely factored, nor is it completely expanded. Right? And that's what would lead you to say, hey, maybe it's worth expanding and then combining like terms afterwards and seeing what happens. So that's what we'll do. Now, this is going to be the beast to deal with, x plus h all cubed. But maybe let's do some side work here, because this is going to be worth just focusing on that one part. X plus h cubed, we're going to literally FOIL all this out here. So what are we going to get? We'll have x plus h times x plus h, and yes, I'm serious. We're actually going to do this. So x plus h times x plus h times x plus h. Start with the first ones here too, or these first two here. X plus h times x plus h. If you just FOIL this first two pairs of brackets out, you'll get x squared plus 2xh plus h squared. That's, if you don't believe me, check. FOIL this out carefully. This is what you'll get. right? And then we'll still have the x plus h after. Okay, and then now it's just a matter of multiplying each of these three terms by x, and then multiplying each of those three terms by h. So let's multiply them by x first. So we're going to have x cubed plus 2x squared h plus h squared x. So that's multiplying all three of them by x. And then if I multiply all three of them by h, I'll get plus x squared h. If I go 2xh times h, I'll get plus 2x h squared. And then lastly, h squared plus h, or pardon me, h squared times h will be h cubed. Okay, so now let's see what we can combine. The x cubed, there's no other x cubed terms. So we just got x cubed. And then now what do we have? We have, well, 2x squared h, but then we have another x squared h here, so we can combine these. So we'll have 3x squared h. So that takes care of these three terms, but then now these three terms, right? We have h squared x, and then 2x h squared. Well, this is the same as x h squared. If I wrote the x, in fact, I probably should have wrote this as x h squared, but it's still fine as h squared x. But notice that these can actually be combined, because they both have one factor of x, and they both have one or two factors of h, so one factor of h squared. So I can write that as 3x squared, and then I have plus h cubed afterwards. Okay? Or if you wanted to use Pascal's triangle or the binomial expansion formula to just go from here to here, if you want to do that, that's fine too. I don't like to memorize all those rules. I like to just do it from scratch every now and again. For how often you have to do it, it's not that bad. But this is what we're going to have. So since we did this all separately, we didn't have to do each one of these steps while writing the limit as h goes to 0, worry about the fraction each time, right? It was straightforward to just work this out. Now we can take all this and plug it in for that expression, and now here's what we're going to get. The limit as h goes to 0, so x cubed plus 3x squared h plus 3x h squared plus h cubed, and all of that is minus x cubed, right, because that term up there, and that's all divided by h. Okay, this is actually better than it looks, because now look at that, x cubed and x cubed, those are going to cancel nicely. So we'll have the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed all over h. And guess what? There's a common factor now of everything in the numerator. This is exactly what we were hoping for. So yeah, we can factor out an h from the numerator. So we'll have h times 3x squared plus 3xh plus h squared. That's what we'll be left with in the numerator. And then that'll be all divided by h. And now the fun part, cancel those h's. Because now, guess what happens? Now, well, first of all, the fraction's gone. That's always a good thing. So 3x squared, or it's always nice and encouraging to see fractions disappear. So that's what we're going to be left with, 3x squared plus 3xh plus h squared. Well, when those h's canceled, it stopped being a 0 over 0 type, right? It's always a 0 over 0 type at this stage. But you can go and check and see every single one of these expressions. If you were to plug in h equals 0, you get 0 over 0 here, 0 over 0, 0 over 0, 0 over 0. They'd all be 0 over 0s. No good, right? But now once those h's canceled, because those h's are really the source of the 0 over 0 problem. Now, once you're here, this is like a polynomial in terms of h. If you were to take h, pardon me, this is a polynomial in the variable h if you were to take x to be constant, right? And as far as this limit's concerned, x is a constant. So this is a polynomial in h. It's a continuous function of h. We can just plug in h equals 0. And guess what? We know where these two terms are going. If you plug in h equals 0 here, you're going to get 0. What about the h squared? If you plug in h equals 0, that's going to 0 as well. So finally, what you get is just the 3x squared. So the answer is dependent on x. But of course, that's what we expected, right? We were talking about the derivative as a function of the function f of x equals x cubed. So f prime is a function of x, so it makes perfect sense to get an answer that's dependent on x. But anyways, so that's how we can finish this off. We can say therefore f prime of x is equal to 3x squared. Finally, we got it. Okay, and that's how we can calculate the derivative of a function. The result is going to be a function now instead. It's not a slope anymore. But it gives you slope, and that's what we're about to see on the next page.